Okay, so thank you very much for inviting me. It's a pleasure to be here. And my journey to think or rethink about sex, brain, and gender beyond the binary started over a decade ago when quite accidentally I ran into a study which reported sex differences in the effects of sex or in the effects of stress on the brain. And specifically, the researchers reported that 30 minutes of stress led to an increase in dendritic spines. So what you can see here is a piece of dendrite, and the small extensions are dendritic spines. And you can see that in males, there was an increase following exposure to stress in the density of spines. And in contrast, they reported that in females, there was a decrease in the density of these spines. For the researchers, this was yet another example of sex differences in the brain. But I looked at these results horizontally instead of vertically, and I noticed that what these results show is that actually sex effects on the brain may be opposite under different stress conditions. Or in other words, what was typical in males under the no stress conditions was typical of females following stress, and what was typical of females that were not stressed was now typical in males following stress. This would be analog to someone undergoing a lot of stress and then discovering that her clitoris turned into a penis, or that his penis turned into a clitoris. Obviously, this never happens with genitalia, but it does happen a lot in the brain. And following this study, I looked and found that there are many studies like this reporting that sex effects on the brain may be opposite under different conditions. So such reversals of sex effects have been demonstrated for many regions of the brain, for many different brain features, and following many different manipulations. Even housing rats, one to a cage or several to a cage, may reverse some sex differences in the rat cortex. And when you look at these studies, what you see is that these interactions between sex and different factors like stress or housing conditions may be different for different brain measures. So the same manipulation can reverse a sex difference in one location, as is here, but abolish or create a sex difference in a different region. And together, these findings challenge the sex binary. Before I explain how they challenge the sex binary, I want to talk a little bit about what these studies do tell us. So what these studies show is that sex-related factors affect brain structure and function. And there are many studies like this showing that indeed sex-related genes, and even more so sex-related hormones, affect brain structure. Usually when we hear that sex affects the brain, we immediately continue to conclude that this must mean that there are male brains and female brains. But these studies suggest otherwise. And again, in a minute, I'll explain why. What you can also see here is that even though sex-related factors affect the brain, and there are sex differences in the brain, knowing someone's sex category, that is whether there are males or females, does not allow us to predict the brain structure. So take, for example, this example here. So knowing that you're going to look on the brain of a male doesn't allow you to predict whether this male will have high or low density of spines. And this is because sex effects interact with other factors. So as I said, together, these studies challenge the sex binary. But it turns out that it's not very easy to challenge the sex binary. And this is because, as Veronica Sands explains, the problem with the sex binary is that there has never been an hypothesis or a theory to test. It is an epistemological framework that runs behind, above, and beyond particular theories and research projects. Within this binary framework, the taken for granted starting point is that there are male and female brains. And therefore, people are always looking for sex differences. And when they find such differences, they interpret them as evidence for the existence of male and female brains. And you can see this self-maintaining belief in the comments of an anonymous reviewer. So they say the usefulness of the dichotomization into male and female brains stems not only from its biological reality. So, you know, we can stop here. It's a biological reality. So what else do we need to do? So the usefulness stems not only from its biological reality, but from the existence, but from the fact that sex differences of all sizes and kinds exist at every level of brain function, not just regarding human brain anatomy. So we see that differences still overwhelmingly warrants categorization of brains as belonging to different, if often overlapping, populations, that is, as female and male brains. And we can see the same logic of assuming or interpreting the existence of sex differences as evidence for the existence of male and female brains in this diagram. So this is a summary diagram, which some of you may know, of a study which looked at the strengths of over 9,000 connections in the human brain. And they found differences out of these over 9,000 connections in several dozens. And this is a summary diagram. So the upper panel shows all the connections that were stronger on average in men compared to women. And the lower panel shows all the connections that were stronger on average in women compared to men. The color code here is blue for intrahemispheric connections and orange for interhemispheric connections. And when you look at these images, it indeed seems that men from Mars and women from Venus. So it seems that we are looking at very different brains. And indeed, the text that accompanies these images also conveys the same message. So they are talking about male brains being this way and female brains being another way. What they do here is assume that what's typical of the male brain or of the brains of men is to have male typical connections. And what's typical of the brains of women is to have female typical connections. It sounds like common sense until you remember that sex effects on the brain, or that what's typical of males and females may be opposite under different conditions. So even if I start at some point with only female typical features, so in this example, let's say with only orange features, then following some kind of manipulation or event, some of the brain features will change their form, others will not, and I will end up with a mosaic of both female typical and male typical features. If we were talking or using this color code, so I will end up with a brain which has both blue and orange connections. So this is the mosaic hypothesis, which I formulated over a decade ago, according to which what would be typical of brains is to have both male typical and female typical features. And a few years later, we tested the mosaic hypothesis in the human brain. Together, we analyzed the structure of over 1,400 human brains, and we looked at gray matter, white matter, connectivity, etc. I'm only going to show you one analysis. In this analysis, we divided each brain into 116 regions, measured the volume of each region in each brain, and wrote it down in a table. In this table, each line represents a single brain, the volume of each of these 116 regions. Then, to appreciate similarities and differences between the brains of men and women, we used a color code. We looked at each brain region, and if this region was relatively large compared to the volume of this region in all other brains, men and women together, then we colored it in green. If it was relatively small, we used yellow. When we were done, this is what we saw. Brains of men on the left, brains of women on the right. Each line, a single brain. Now, you don't need statistics to see that there are differences between the brains of men and women. At the group level, there's more green at the women's side and more yellow at the men's side. But you can also see that brains are rarely all green or all yellow. Instead, each brain is a unique mosaic. No two lines are the same, of green, which is more common in women, and yellow, which is more common in men. In other words, my question is not whether there are sex-gender differences. We can see here that there are sex-gender differences in the human brain. I'm also not interested in the source of these differences, whether this is nature or nurture, but only in whether they add up to create two types of brains, female and male, as is often implicitly assumed to be the case in the human brain, or do they mix up in each brain to create these brain mosaics? And I think that when you look at these images, the answer is very clear. So if brains are not male or female, how best to describe the relations between sex and the brain? So this was a question that we worked in two different studies. And again, I'm going only to show you the result of only one such analysis. In this analysis, we asked whether the typical male brain is indeed different from the typical female brain, as is often assumed, or whether what's typical of both men and women is to have this mosaic of male typical and female typical features. And to answer this question, we used a machine learning algorithm, which is called anomaly detection. So in anomaly detection, the general principle is you take some data set with some examples and you train the algorithm on this data set. And then you give the algorithm new examples. And for each new example, it needs to decide whether this belongs to the original data set, so whether this is normal compared to the training set, or whether this is abnormal. So we use this, but instead of just training on some arbitrary data set, we trained the algorithm on the brains of one sex category. So let's say on the brains of women. And then after the algorithm learned what's a normal female brain, we gave the algorithm new brains of both men and women that weren't included in the original data set. And for each brain, it had to decide whether this brain is normal compared to the training set comparing to female brains. And of course, then we repeated the same analysis, but this time training first on the brains of men and testing on the brains of men and women. What would be the predictions? So if the typical male brain is different from the typical female brain, then we expect that if we train on the brains of women, then many more brains of women would be classified as normal compared to brains of men. And of course, the other way around if we first train on the brains of men. However, if we are right, and what's typical of both men and women is to have this mosaic of male typical and female typical features, then it doesn't really matter whether you train on brains of men or women, because in both cases, you will be training on human brains. And therefore, when you test for new brains of men and women, the algorithm is supposed to classify the same number of brains of men and women as normal or as abnormal. So we have very different predictions with this approach, which is good for science. Before we tested this approach on the brains of on human brains, we first wanted to make sure that the algorithm could detect two populations if they existed in the data. And to do this, we looked at the facial morphology of two primate species. So obviously, we have here two populations, two primate species. And for all the analysis that I will describe, we always looked at the data in the original high dimension space. In this example, it was 190 features, and following different methods of dimension reductions, both linear and non-linear. I'm not going to go into this. This is just to make sure that our results are not the result of some specific mathematical approach. So let's go over the results together when we train the algorithm on facial morphology of two primate species. So let's look at the case when the algorithm was trained on the facial morphology of macaques. So we can see that all dots, all runs of the algorithm fall on the y-axis, which means that the algorithm never mistakenly thinks that a capuchin is normal when it was trained on macaques. And similarly, when the model or the algorithm is trained on capuchin, then the algorithm never thinks that a macaque is normal. Okay, so the algorithm never misclassifies one species as belonging or as a normal example of the other species. So the algorithm does a good job in detecting two populations when they do exist in the data. What will happen when we do the same, but this time train on human brains? Okay, so we do the same, but this time train the algorithm either on females or on males. And you can see that the results are exactly the opposite. So instead of being on the X and Y axis, all the data points fall along the Y equals X axis, meaning that regardless of whether you train on the brains of men and women, the number of men and women that are classified as normal is very, very similar. And this is also true for another data set. With this analysis and several other approaches, altogether we analyzed the structure of over 20,000 human brains. And what we showed with this and other approaches is that the brain architectures that are typical of women are also typical of men, and vice versa, that there are large sex-gender differences in some rare brain architectures. And this is important if you want to think about some large sex-gender differences in some psychopathologies, for example, autism. So this type of, so autism is obviously a rare brain condition, and our findings can explain why you can see large sex-gender differences in some rare phenomena, even though the typical male and female brains are not different, but rather what's typical of humans is this mosaic. And the last thing is that we showed that sex category provides very little information on brain structure. And I want to remind you the dendritic spines that we looked at in the beginning. So even though sex-related factors affect the brain, we saw that sex category doesn't predict or doesn't allow us to predict the density of spines. We showed that this is also true for the entire brain. So knowing someone's sex category provides very, very little information about the structure of someone's brain and about how their brain would be similar or different from the brain of someone else. And I want to stay, okay, so I will come back to this point in a minute, but just going back to this image, which I think is very important, because usually when we hear that there are sex differences or that sex-related factors affect the brain, we immediately conclude that there must be male and female brains. And I think this image helps us create a new framework instead of the binary framework, because we can see that there are differences in the group level, but we can also see that each person is a mosaic. So under the binary framework, we can only ask, are men and women the same or different? But when we look at these images, we can think of a different answer. Men and women are neither the same nor different. We are all different. No two brains are the same. And this is important, sex category provides little information on how we are similar or different. And just to give you an impression of what I mean by sex category provides little information on how we are similar or different, we looked at the volume we looked at the structure of over 20,000 brains. And what we did is look at the distances between every two brains. So we can calculate the distance between every two brains of women, every two brains of men, and every pair of a man and a woman's brain. And you can see here the distribution of distances. And let's go over this together. So on the x-axis, you see the distance between brains. And first, we can see that the distances are very, very large. So the smallest difference starts around 15 standard deviations. So the brains are, this can give you an example or a feeling of what I mean when I say we are all different. If you think of brains in a multidimensional space, they are very different, very far one from the other. Let's look at the distribution of the different pairs. So let's start with women. So women are in red, and we have two distributions for women. One is in solid line, is the distribution of the distances between every possible pair of two women. The other red and dotted, is a distribution of any possible pair between every woman and every man. And you see that the two lines, the two red lines, are exactly overlapping, which means that the distances between every two men and every two women and every woman and man are exactly the same. This is what I mean when I say that sex category provides little information on how we are different or similar to someone else's. My brain is not more remote or different from a brain of a male than from a brain of a female. And you see the same for men in blue. So the two lines for the men, again, are exactly overlapping. So men are not more different from women than they are one from the other. Another way to look at this is to look at the distances between every brain and the average male and female brain. So let's look at this together. So again, I want you to notice that the distance between the average male and female brain is about 1 standard deviation, which would be quite large if we were looking at a single dimension space. But multi-dimension space does not behave as a single dimension space. So let's look at this together. And actually, let's start from the unidimensional space. In a unidimensional space, to normal distribution, the distance between the means gives a lot of information, because most of the observations fall around the mean. So you can see that here is the mean, and most of the observations fall around the mean, both of the green and of the blue distributions. However, if we look at a multidimensional space, this is very different. So you can see that around the mean, there is no observation. No brain is around the average male or female brain. You can see that brains start to appear around 9 standard deviations away from the average. So in a single dimension space, most of the observations fall between plus minus 2 standard deviations. In a multidimensional space, there is nothing around the means. They give no information. The average female brain does not exist. No one has an average female brain or an average male brain, not even something similar to an average male or female brain. If we look at the distances again, so let's start again with women. So you can see again that the distances between every woman and the average female brain in solid line and every woman and the average male brain in dotted line are very, very similar. And this is also true for men. So the distance that does exist between the average female and male brains gives no information, because the distribution of distances of women from these two averages is the same. And this is also true for men. So I hope that now you get a better understanding of what I mean, that the binary framework is very misleading when we think about sex and the brain. Because first, we are all different, so no two brains are the same. And sex category provides very little information on how we are similar or different. So the binary framework is very misleading when thinking about the brain. Let's now look at sex itself. And sex itself, we can think of sex-related genes and sex-related hormones. And I'm going to talk about the hormones. Because when we're talking about sex affects the brain or sex differences in the brain, what creates these sex differences in the brain, for example, is most often sex-related hormones. It's not our reproductive system. It's not whether we have a male or female genitalia. When we think of sex-related hormones like testosterone, estradiol, or progesterone, often we use a binary framework and we think or talk about male hormones and female hormones. But this is a very misleading framework to think about hormonal sex. Because first, these hormones appear in all humans. They are created by both types of gonads as well as by other brain tissues like adrenal glands, for example, or fat. So we all have all these hormones. The average levels of estradiol and progesterone are quite similar in humans, males and females. And with the most notable distinction is of obviously pregnant women. So pregnant women are a class of their own. that non-pregnant men and women have very similar levels of estradiol and progesterone. There are differences in the average level of testosterone in some parts of our lives. So, for example, not in children, maybe not in very old age, but in reproductive years, the average level of testosterone is higher in males compared to females. But still, there is some overlap. And you can see this, for example, in this study. And even more importantly, the average level of hormones is very, very dynamic. Usually, we think of these changes in the level of hormones with regard to females' menstrual cycle. So how the levels of hormone changes throughout the month. But the levels of hormones are also changing in males. And this is an example from mice in this time. Each panel here shows the levels of testosterone in the dotted line throughout a single day. And you can see that the levels fluctuate dramatically from a very low baseline level to a very high peak. And that you can see that the number of peaks and when they occur during the day may be different between different mice. So the level of testosterone are also changing all the time. Now, these changes in hormones are not only caused by some internal factors, like, for example, menstrual cycle, but also these hormones are responsive to behaviors and to events in the environment. And, for example, competition, sexual thoughts, and parenting all affect the level of testosterone. So, again, we see that this idea of, or this binary framework applied to the hormonal sex misleads us to think that there are male and female hormones, when in fact we all belong into a highly dynamic and variable phase of these hormones, when we often overlap, and this is always changing. So the very stable idea of a male and a female sex in terms of hormones is, again, completely irrelevant. What about gender? So we can ask, are there men and women, not in terms of the existence of two reproductive systems, males and females, but in terms of the psychological and behavioral characteristics? So we know that there are differences between human males and females in cognition, personality, behavior, interests, etc. Again, I'm not asking about the source of these differences, nature or nurture, but would only want to know whether these differences add up consistently within each individual to create two types of humans, women and men. So to answer this question, we again did an analysis very similar to what I showed you with the brain. This time we looked at data sets that reported sex differences or sex gender differences in whatever variables that they found. And we selected from each data set only the variables showing the largest differences between women and men. And for each of these variables, we used again a color code, this time between pink and blue. So pink would be scores that are more common in women compared to men, and blue would be scores that are more common in men compared to women. So if we just take the example of this study, so there was a difference between men and women in how much they worried about their weight. And in this sample, women worried about their weight more than men did. So high scores would be considered feminine in this sample, whereas low scores would be considered masculine. So here again are the results. So each line here represents the 7 characteristics in a single individual. These are men and these are women. There were more women in the study. This is why we have 2 panels for them. And again, you can easily see the group level differences. There is more blue at the men's side and more pink at the women's side. And this has to be this way because this is how we define what's blue, what's masculine, and what's pink, what's feminine. You can also see that there is quite a lot of pink in the blue and quite a lot of blue in the pink. Again, this is also known for any psychological variable. There is some overlap between men and women. So some men would be feminine in this characteristic or variable, and some women would be masculine. What we wanted to know is whether there are blue and pink individuals. And there was not even a single individual in this sample that had only masculine or only feminine characteristics. Most individuals were highly masculine on some variables and highly feminine on others. So we can see that also in terms of our psychological and behavioral characteristics, humans do not belong into two types the way they do in terms of their reproductive system. We also looked at sexual attraction, so a variable obviously showing large differences between men and women. And we asked each individual, and you can think of your answer to yourself, we asked each individual how much they are sexually attracted to men and how much they are sexually attracted to women. And you can see the results here. So the size of the circle is proportional to the number of, to the proportion of individuals from this specific gender category. And what I want you to appreciate here is the huge variability in sexual attraction in humans, how we do not fall into 2 or 3 distinct categories of heterosexual, homosexual, and bisexuals, but rather humans can be found on each possible point on this 2-dimensional space. And similarly for gender identity. So we asked individuals how much they feel as a man and how much they feel as a woman. Again, you can give yourself your answer. So think of a scale between I never think of myself as a man to I always think of myself as a man, and similarly, I never think of myself as a woman to I always think of myself as a woman. And this is the results of an Israeli sample of over 2,000 individuals. And you can see that obviously more women think of themselves as women and more men think of themselves as men. But you can see that also many individuals think of themselves sometimes as men and sometimes as women. And these are all cisgender men and women. So these are individuals who self-identify in a very normative way. But still, the gender identity is much more complex or variable or beyond the binary than we usually assume. And we found something very similar in another larger study of English-speaking people. So again, what I want you to appreciate here is the huge overlap between the different groups and how variable humans are. We've recently launched a website, the Gender Mosaic Questionnaire, in which individuals can answer a set of questions and then receive their own gender mosaic. So they can see how feminine or masculine they are on a set of variables. Now, obviously, what's feminine and what's masculine varied or changes across cultures. So let me explain how we define what's masculine and what's feminine. So let's look at this question. And again, you can choose your answer. So when choosing a romantic partner, how important is it that your partner is rich? So this is a question, and you can answer between unimportant to indispensable, very, very important. And this is a distribution of the answers of a sample of 1,500 people from Japan. And we can see that there are differences between the answers of men and women. So scores 2, 3, and 4 were more common among women than among men. So we can say that these are feminine, or if you scored 2, 3, or 4, your score was feminine. And we can use the color code of red or pink. In contrast, answer 0 was more common in men compared to women. So it may be considered as masculine and colored in blue. Answer 1 was similarly common in men and women. So it is neither feminine nor masculine. It is gender neutral. And if you scored 1 or chose 1 as your answer to this question, then your square for this question would be yellow. It seems simple, but if we consider another population or another sample, we see that things can change. So for example, if we look at the sample of 1,500 people from the United States, we see that there are hardly any differences between the answers of men and women, making all answers gender neutral. So in this case, regardless of what you chose, and you chose the answer already a few minutes ago, so regardless of your choice, if we compared your answer now to the American sample, then your square will be yellow. And you can see here, this is my gender mosaic when my answers were compared to the American sample. And you can see how my mosaic changes when my answers are compared to the Japanese sample and then to a sample from Israel. Now, remember, my answers haven't changed. What has changed is their definition as feminine or masculine according to the different samples. And of course, I'm not the only person that is mosaic. So you can see here the mosaics of some of the people that already answered the questionnaire. And you can see that each individual is a different mosaic of both feminine, masculine, and gender neutral characteristics. So an interesting question, and I will not go into this, but just leaving you with the question is, why do we perceive humans as men and women when in fact each of us is a unique mosaic of feminine and masculine characteristics? And the short answer for this is that we perceive humans as belonging to two categories, even though obviously they don't, is because this distinction between men and women is central to many human cultures. And because of this distinction, we label individuals who are female or male differently, we treat them differently, there are different cognitive biases, etc. And if you want to read, then we've written about this. And the only thing I want to say a few words about is that you can see that in this self-maintaining gender binary cycle, in which a gender binary social system self-maintains itself, even though individuals do not belong to two binary genders, you can see that an important component is some kind of a biological essentialist view of gender. And I want to talk a little bit just about this, about the myth of the male and female brain. So the myth of the male and female brain, and in earlier times, the myth, religious myth about the fundamental difference between men and women. So this myth is a critical part in explaining or maintaining this binary social order. And this myth is as old as modern science. And already in the 17th century, scientists tried to explain why men are superior to women. And it seems at the beginning as a very easy task, because they noticed that men on average have larger skulls than females than women. And they couldn't yet measure the brain because they didn't have the technology, but they already knew that the brain is important. So they used the size of the skull as some kind of a proxy for the size of a brain. So if men have larger brains, then we can understand why men are intellectually superior to women. Easy. As long as you don't remember that some kind of animals like whales and elephants have much larger skulls than humans. So obviously the male scientists that wanted to explain superiority of men over women didn't want to claim that whales are superior to humans. So they had to find a solution to this. And they found it in thinking, instead of the size of the skull, talking about the ratio between the size of the skull and the size of the body. And indeed, when you use this measure, humans have a larger ratio, skull to body ratio, than elephants and whales. Okay, so now we have that men are superior to whales and elephants. Okay, good. But it turns out that women have a larger ratio of skull to body than men. Now, if you think that the scientists then said, okay, so now we understand that we were always wrong, and women actually are superior intellectually to men, and let's just change social order to reflect this. No, this didn't happen. Instead, they had to find out, or to come out with a different solution or explanation of how women can have a larger ratio of skull to body, but still be inferior to men. And this was found in looking at the ratio of skull to body in children. So they noticed that this ratio is very big in children. So what they claim now is that in humans, the normal development is from a large skull to body ratio to a small skull to body ratio, and women are just stuck in the middle between the child and the adult. In the 19th century, when they could already measure the brain, they noticed that the brains of men are on average larger than the brains of women, which is indeed true. And this led them to explain, or this was used to explain why, for example, women can go to universities. And some scientists even thought that it would be dangerous for women to go to universities. It could damage the brain, or it could lead to the flow of blood to the brain instead of the reproductive system, and affect or disrupt the reproductive capacity, etc. So they have many different explanations of why women shouldn't go to university. Obviously, at that time, women could not indeed go to university. They were not allowed to go to university. Nowadays, when for many years now, women outnumber men at all levels of academic education, first degree, second degree, PhDs, it seems ridiculous that someone could have claimed that women cannot go to universities because their brains were smaller on average than the brains of men. Now, don't get me wrong. Women's brains are still smaller on average than male brains. But obviously, this is not a reason why they cannot go to university. And coming back to our century, so still we have the myth of the male and female brain. It is just more sophisticated because the methods that we have now, or the tools that we have now to measure the brain are much better than they had in the 17th or 19th century. But the logic is still with us. We look for differences between the brains of men and women, and then when scientists find them, then they think that there are male brains and female brains. And I hope I managed to show you that this is not true. This is just a wrong conclusion, which is based on a binary pre-assumption. Okay, so I will stop here. So we have time for questions, and you have everything in front of you, all the things that we discussed. And I want to thank you for listening. And Alexandra, I pass it to you.
Okay, thank you very much, Professor Joel, for the presentation. I believe that it stimulates our curiosity to this topic. And the idea about the questionnaire was also interesting. So let's go to the Q&A section. So we have a question relating to the autism spectrum disorder. In your presentation, you pointed that there are large sex gender differences in some rare brain architectures. Lately, there are growing information about people with ASD can more likely identify as non-binary. So could you tell more about this topic, about the relation between sex and the brain in this case?
Yeah, so we haven't tested people with autism. And what I said before, this is just a way to explain it, but we haven't tested whether this is the case. This is more a contra-suggestion or an alternative hypothesis to a very dominant theory, which claimed that autistic brain is an example of an extreme male brain. So within this hypothesis, the extreme male brain hypothesis of autism, the typical male brain is considered a little autistic compared to the typical female brain. And what we show is that you do not need to assume that typical men are a little autistic compared to typical women to account for the sex gender difference in the occurrence of autism, or more accurately, in the diagnosis of autism in men compared to, or boys compared to girls. We do not study the relations between ASD and gender identity. So although I am aware of these reports, I have nothing to say about it because we haven't studied it.
Yeah, of course. And do you have maybe some literature on this topic to suggest for our audience?
No, I'm not familiar with this, so I don't know. I know the statistics, but I don't know. And I don't know whether it's not related to the general increase in the number of people that self-identify not as cisgender men or women, but in other ways, as transgender, non-binary, etc. So we see a change throughout, or in many cultures, and not only in people with ASD. So I wouldn't make too much of this observation. Let's see how stable it is, etc.
Thank you. So the second questions from our audience is, do you think that there are more relations here with neurodiversity?
I'm not sure I understand.
Okay. I don't know what the author of this question have in mind.
So maybe
So-
whoever wrote it could write again in more detail, and we can come back to this later.
Okay, so another question. We have, are there longitudinal studies on how those gender brain features change in time? Same with gender identity.
Okay, so we haven't conducted long-term studies like this. I can say that sex differences, both in animals and in humans, are different throughout life. So in humans, for example, there are hardly any sex-gender difference in newborns, and most, except for the difference in size, which we already see in newborns. But when you take this into account, there are hardly any differences between the brains of newborns, male and female babies. And most of the differences in humans appear around puberty. So they appear later in life, and they change throughout life. So some of them may grow larger, some of them may disappear in older age, etc. And also in animals, in rats, there are different sex differences in different times throughout life. So this suggests that the brain mosaic will continue to change throughout life, because we know that, and this is what I showed you before, that the different experiences are affecting our mosaic. So throughout life, as we experience more and more experiences, our mosaic will continue to change. But this is, again, we haven't tested this. This would be interesting to test, but we haven't tested this.
Okay, thank you. And I don't see any related comments to the previous question. So I think we must skip it. And it was the last question for now. So maybe if it's possible that if any will show later, because your lecture will be online as a in the YouTube. So maybe we can send you a question if any occur.
Yeah,
Okay.
you could. Yeah.
Okay. So thank you very much. It was a really inspiring lecture.
Thank you very much. Bye.